Afternoon, everybody. I'm Peter Sarnak. I'm from the School of Math, faculty in the School of Math, and it's my great pleasure to introduce our speaker today, Cynthia Rudin, who is involved in our Women in Math program as the Turn lecturer for 2022. And as part of the Women in Math program, we usually have, or sometimes have, if there's a good reason for it, a semi-public lecture, which is what this is. So we have people on Zoom, and we have quite many people who are probably not directly involved with the program. And the topic, I think, is very interesting, so it should appeal to a wider audience. Cynthia is a professor of computer science, electrical engineering, and computer engineering, statistical science, mathematics, and biostatistics, and bioinformatics at Duke University. That's quite a lot of departments, or was it one department? I'm not sure. She's an alum of our Women in Math program, so it's great to have her back here. She's also an alum from Princeton University, where she got a PhD in the program for applied mathematics and computational mathematics. The title of her thesis, Boosting Margins and Dynamics, and her advisors were Ingrid Derbyshire and Robert Chapin. She has won many, many awards. She's one of the world's leading artificial intelligence and machine learning researchers, and she's a winner of the Squirrel AI Award for Artificial Intelligence for the benefit of humanity from the Association for Advancement of Artificial Intelligence, one of the most prestigious awards in artificial intelligence, and comes with a handsome amount of money. So it's a great pleasure to have her speak today. And the title of her talk is Stop Explaining Black Box Learning Models for High Stakes Decisions and Use Interpretable Models instead. I'm sure we'll learn what they are. Thank you and welcome.
Thanks. All right. So I want to make the point that there are bad things happening now. There are bad bail and parole decisions being made because people type the wrong number into a black box model, and it's letting dangerous people go free, and it's keeping people in prison who don't deserve to be there. We have bad medical diagnosis and screening algorithms that make decisions based on factors that are not allowed. So for instance, in this article, they talk about an algorithm that makes decisions based on like words in the medical image instead of the medical content of the image. We have also bad loan and credit decisions being made based on faulty information. It's very difficult to get this fixed. And I claim that explainable machine learning perpetuates this problem. Okay, so some definitions. So an interpretable machine learning model obeys a domain-specific set of constraints that makes its computations easier to understand. So interpretable machine learning models are constrained. So as you can figure out, an interpretable machine learning model is where you use a model that's not a black box. Okay, so you want to contrast that with explainable machine learning. So interpretable and explainable, they sound the same, they're completely different. In explainable machine learning, you use a black box model that a human can't understand, and then you try to figure out afterward what happened to it. So you start with a black box, and then you would create another model that approximates it or compute derivatives of it, or you visualize what part of the input the model's paying attention to. You basically do some calculation that makes an excuse for why it's okay to use that black box. All right. So, and interpretable models, there's a broad variety of them. So you can constrain the models in different ways. So you can have fully interpretable models where you can understand how all the variables are jointly related to each other. It's very sparse models. To sort of loosely constrained models where, for instance, like the model is forced to increase along certain variables. Now, I know these things sound the same, like interpretable, explainable, they sound almost identical. And so a lot of people really don't understand why there's a giant chasm between these two things and why there's you know, people kind of on either side of this chasm here. Okay, so why is it that I say that we should not be explaining black boxes and we should be using interpretable models only? So there are a couple of important reasons. The first one is that we don't need black box models in the first place, and I'm going to talk about that soon, but well, for the remainder of this talk. Well, it turns out that you can get accurate models that are just as, or interpretable models that are just as accurate as the black boxes. And also the explanation methods, they actually tend to lend authority to the black boxes. And so it sort of makes an excuse for why you can use it, but the explanations are flawed. Okay, so I want to, I put this slide up a minute ago, but I want to get back to it. And in this article, so this is an article about Glenn Rodriguez, who was in prison since he was a kid, basically. And he comes up for parole a whole bunch of years later. And he was a model prisoner, and he was denied parole because his COMPAS score was miscalculated. And COMPAS is a black box model that's used widely throughout the US justice system. And it's a proprietary model, so we don't actually know how complicated it is, but it involves up to 137 factors, because that's what the score sheet has on it. And his parole was denied because when he compared his score sheet to someone else's after his parole was denied, he realized that there was a typo in his criminal history features. And it's not just him that this happens for. I've seen this, I've seen a lot of cases where people's scores are miscalculated because since the model's proprietary, you don't actually know what actually matters in it. Okay, so I was just wondering, like, you have this black box model. It's a company that sells this model to the justice system. How accurate is it? So we had some data from Florida that was made public a few years ago. And that data can tell us how accurate this model is, because we had COMPAS scores for all of these people from Florida. So when that data set came out, we took the COMPAS scores and the features about each person's criminal history and age and demographics and so on. And we were able to compute exactly how accurate it is. And we were able to compare it to the latest machine learning method in our lab that we developed at the time, which was called Corals. So Corals is certifiably optimal rule lists. And this method, this is just a machine learning method, and it produces optimal one-sided decision trees, whereas that one is proprietary. We don't know what's in it. So anyway, we launched Corals at this data, and the machine learning model that it created was so small that it fits on the bottom of a PowerPoint slide. So this is the model. It says if the person's age is 19 to 20 years old and they are male, then predict arrest within 2 years of their COMPAS score calculation. Also, if they are 21 to 22 years old, so a little bit older, and they have 2 to 3 prior offenses, then predict arrest. So if they're a little older, but they have some priors, predict arrest. Also, if they have more than 3 priors, predict arrest, otherwise predict no arrest. And we looked at this and we thought, that's quite small. Like, could this actually, compare to the accuracy of that thing, right? That's proprietary. It was built from a very large data set. This thing is just, an optimal sparse decision tree. Could it be as accurate? So we did the comparison, and lo and behold, it was. So this is tenfold cross-validation, which means we're testing on part of the data set and evaluating on the other part. And so each color is a different test set performance. And as you can see, across the board, all of the folds seem to be similar for COMPAS and Corals, okay? So I thought, that's interesting. Well, let's see if we can get any more accuracy on this problem. We'll just throw the whole machine learning arsenal at the problem. And so we ran a whole lot of different algorithms, and they all perform the same. And some of these are very complicated, models, like, for instance, support vector machines where you project the data into infinite dimensional spaces and do some computation there with kernels, and then you've got boosted decision trees that combines a whole lot of decision trees together, hundreds of trees together. So you can't fit the formulas for those models on a slide. Whereas, on the other hand, Corals' whole model is right there in the corner of the slide, okay? And they're all equally accurate. Now, there was a huge debate in the literature and in the media about the algorithmic fairness of the COMPAS model. But the truth is that we just don't seem to need COMPAS at all. So, I just wonder why we're still using it. Okay, so the more work I've done in the field, the more I'm convinced that for high stakes decisions, there really doesn't seem to be an accuracy interpretability trade-off. Lots of people think there is, like the intuition that there is, like you use a more complex model, you do better, right? But there's no scientific evidence for that. Now, case in point, this image from the DARPA Explainable AI BAA. Okay, so this was written by, I don't know, DARPA program manager, something like that. And they were trying to present to us an idea of the accuracy interpretability trade-off, right? That, if you're really accurate, then you can't explain very well. And if you can explain really well, you couldn't possibly be accurate, right? Okay. Now, I have some issues with this figure. The first one is that it's not clear what these axes actually mean. How do you measure learning performance? How are you measuring explanation effectiveness? What data set is being used here? So this is just matheism. It's just sort of, it's just like a junk figure. It's like somebody drew it with a Sharpie. Okay, and then another issue I have with this figure is that it seems to be illustrating a number of experiments with a static data set and a fixed evaluation metric. Like you ran a bunch of algorithms on a fixed data set with a fixed evaluation metric. That's what you got. The problem is that is not how data science is actually done. Data science, if you are a data miner, you would be familiar with the process like the knowledge discovery process. This is the knowledge discovery process from 1996, and data mining is one step in that process. And what you're supposed to do after you do the data mining is interpret the results and try to understand what's going on and use that information to go back and fix your data set and fix your evaluation metric. And if you don't understand what's going on, you can't do that effectively. So the whole idea that we would be using a static data set with a fixed evaluation metric is just not the way we do data science. And in fact, if you can actually understand what's going on, that whole process of fixing your data and doing data mining, it actually improves your performance. So in that sense, this figure is actually reversed. Like you should have better explanation effectiveness, better learning performance with better explanation effectiveness, because you can understand what's going on. Now, in reality, also, the trade-off doesn't happen like this. And on the previous slide, I showed you exactly an example with COMPAS where we did all of those calculations with all of those different machine learning methods, and it's completely flat. Now, there is some subtlety in this information, which is, if you're working with something like computer vision, where you need to use a neural network, but I'll talk about that later. In any case, for tabular data, it seems to be pretty much flat. Okay, and then also, I couldn't even figure out whether they were talking about explaining black boxes or building interpretable models, because if you're explaining black boxes, you can see a curve like this because you have some approximation error when you're explaining a black box. Like if you're building an approximation to it, you'll see some approximation error. So you definitely could see a curve like this. And so didn't even talk about which one they were doing because I don't think they knew. Anyway, so as I mentioned, there is this subtlety, which is that there's really two types of problems in machine learning. It's almost like two different fields of machine learning, to be honest. There are problems with tabular data, which look kind of like that, like that's a medical example there. In this type of data, all the features are interpretable. Lots of problems in criminal justice, healthcare have data that looks like this. And on the other hand is raw data, which is like images or sound waves or large amounts of text. Now here you don't have a good data representation, but there you do. And the thing is with the raw data, the only technique that's working right now is neural networks, whereas for tabular data, it's a completely different story. With tabular data, as long as you're willing to do some minor pre-processing to clean the data up and build features from it, then all the methods tend to have similar performance like what I was showing you with the COMPAS data. And in fact, that opens up kind of an opportunity to create very, very sparse models like sparse decision trees or sparse scoring systems that get to the same level of accuracy as the best of the black boxes. Okay, so we really have an opportunity to create simple models as long as we can optimize them well. So I want to next show you a machine learning model that is interpretable, can fit on a screen, that is used in a very high stakes decision-making setting. And if you were here in my lecture yesterday, you will have seen this model before, okay? All right, so this model helps to prevent brain damage in critically ill patients. So let's say that you have an aneurysm in your brain and it bursts, okay? So you have a brain hemorrhage, you have blood that's sort of leaking into your brain, which is what's shown over there, that blue arrow there. Okay, so you're in really bad shape. So you get to the hospital right away, get surgery, placed in the intensive care unit. And at that point, you'll have EEG monitors placed all over your head. And those monitors are detecting for the possibility that you might have a seizure. Now, seizures are common in these patients. About 20% of critically ill patients get seizures. Seizures are quite dangerous. They lead to brain damage. They lead to death. And the only way to detect seizure-like activity is through EEG monitoring. Now, EEG is also kind of limited. There's never enough monitors or doctors to go around reading those monitors. And so what happens is that the doctors will often leave patients on there way too long, which prevents patients who potentially need them, these monitors, from getting them. And doctors will do a lot to try to prevent you from getting a seizure. Like they might even give you some medication to actually shut part of your brain down so that it doesn't destroy itself by having a seizure. And also I should mention that these seizures are not things that are outwardly visible. Like the patient is not shaking. This is all totally inside the patient's brain. They're subclinical seizures. Okay, so I work with neurologists and we designed a machine learning model called the 2 helps 2B score, which is a generalized additive model. And it's small enough that it can fit on this PowerPoint slide, but it is as powerful as our best black box machine learning models for this data set. Now, 2 helps 2B, it's called that because it's 2H, E, L, P, S, and then 2 points for the B, so that the doctors can memorize the whole model just by knowing its name. 2 helps 2B was not created by doctors. It was, I know it looks like a rule of thumb, but it was actually created by data fed into a machine learning algorithm. It is a machine learning model. It's just as accurate as the best black box models for this data set. And the thing is, it doesn't force you to trust it. Black boxes force you to decide whether or not to trust them. This one, the doctor can decide themselves whether they want to trust it. And they can also calibrate the score with information not in the database. So if there's a patient who, the doctor looks at the patient and says, oh, there's something weird about that patient's medical history, I think that deserves like 1 more point. So they can add 1 more point to the patient. Okay, now, the score can also be explained to non-physicians so that they can understand like why someone's being taken off of EEG, for instance. And there are only 6 variables in this, but those 6 variables were chosen from this very large number of variables. There were over 70 variables in the data set to choose from. And the optimization problem that was solved for creating this model looks like this. And I'm not going to, I don't need to understand all this math, but what I can tell you is it's a balance between accuracy and the size of the model. So the first term says make it accurate, second term says make it small, and then the constraints say, could you please give me integer coefficients so that I get 2s and 1s rather than sort of 30.56 or whatever. And it has to choose small numbers between -10 and 10. It just happened to choose 1, 1, 1, and 2. So if you are an expert in optimization, you'll immediately recognize that this is a mixed integer nonlinear program. So it's actually a computationally hard problem. But my point is that this should be a problem for computer scientists or mathematicians or statisticians and not doctors. Okay, so so now when you see the 2 helps 2B, you can understand that all of these things like this, all of the selection of the features, this 2 Hertz threshold, all of these point scores, this was all chosen by an algorithm solving a combinatorially hard problem. Okay, so now what happens is that the patient comes in with their aneurysm that's burst and their hemorrhage, and they go to get surgery, and they end up in the intensive care unit with the EEG monitors, then the doctor, the neurologist, can read the EEG and say, oh, this patient has this, this, and that. They have a HELPS 2B score of 3. Therefore, we're going to place them on continuous EEG for at least 72 hours and start them on preventative medications for seizures. Now, so far, 2-HELPS 2B has been validated on an independent multi-center cohort. I was not actually involved in this validation study. This was done by neurologists. And so what they did was they collected data from this totally different cohort and from different hospitals. And then they plotted the predicted probability of seizure versus the true probability of seizure. And the initial data that we built 2-HELPS 2B score from is in blue here. And then green is the validation study data. And so this is predicted versus true. So we want it to be on the diagonal. And you can see that everything is sort of nicely on the diagonal, and it generalized well across these different institutions. So that gives us a lot of confidence in the quality of the predictions. Now, it's been implemented at several different hospitals. And in the validation study, it resulted in a substantial reduction in the duration of EEG monitoring per patient, which allowed the doctors to save, to monitor 2.82 times more patients, which according to the doctors helps them save lives and prevent brain damage. So it's a rare example of a case where a machine learning model is used in a very high stakes decision-making setting, right? This is an intensive care unit with critically ill patients. And the only reason that this could happen is because the model is interpretable. All right, so I've talked about tabular data. I'm going to switch over to talking about raw data for a while, because as I mentioned, for raw data, we really need a neural network. And so the question is, can we actually design an interpretable neural network? What would that look like? Or do we have to create a black box and explain it? So I want to tell you we have a couple of attempts on interpretable neural networks, and I want to tell you about one of them. But before I do that, I want to tell you what we're not doing, okay? We're not doing explanations with saliency maps. So saliency maps, this is a really popular way to create an explanation for a neural network. Okay, so what people do, they say, okay, there's my test image. It's an image of my test set. My classifier classified it as a Siberian Husky. That's great, it got it right. Let's see the explanation for why it did that. And so what it'll do is highlight the part of the image that it thinks it's using to classify the image. And indeed, it classifies the correct part of the image for knowing that this is a Siberian Husky. And so we say, oh, we're very excited because it gave us the right explanation, which means we think it's, we think we trust it, but then we look at what else it's doing, okay? So this is the prediction of the same image as a musical instrument, and it's highlighting exactly the right part of the image as the same part of the image as before. Okay, so it's giving you exactly the same explanation, but the prediction is wrong, and I have no idea why. Okay, so it's not a type of explanation I really like, as you can figure out. And this is particularly bad, unfortunately, for the methods that are being used in radiology right now, which I'm very concerned about that. So there's a tremendous amount of work trying to produce these ridiculous saliency maps that are post hoc explanations in radiology, and I'm quite concerned about what's going on there. And so sometimes you see these explanation methods also that give you the wrong result. So they might highlight all over the place when actually the neural network is using one specific piece of information. So it can be very misleading. You've got to troubleshoot both the saliency map algorithm and the original neural network when you do this sort of thing. Okay, so we were thinking okay, what would an interpretable deep neural network actually look like? So our first attempt at this is to do what's called case-based reasoning. So case-based reasoning is kind of like k-nearest neighbors, where you sort of try to find images that are near the one that yours is, and use the information about those neighbors to figure out your prediction. So, but ours is not exactly k-nearest neighbors. It's sort of like k-nearest parts of prototypes. Okay, so case-based reasoning, by the way, this is like what Dr. House does on television. I don't know how many of you watch Dr. House. I love that show. But basically, Dr. House, he's a TV doctor, and he sees a patient, and he says, "Oh, that patient has a green foot." Well, I've seen a patient with a green foot before. That patient had chilblain. Maybe that patient has chilblain too. Or like that patient has a particular heart condition. That reminds me of a patient that I saw 20 years ago. Maybe, maybe the patient has the same heart condition. All right, so here's what my network, this is my network explaining to me why it thinks this bird looks like a clay-colored sparrow. And I love working on the bird watching data because I know nothing about birds. So what this network does is it takes the bird and it highlights different parts of the bird. So here the highlighting is just done in two different ways. So there it's highlighting the head of the bird. Here's like the edge of the feathers and the belly, and same over here. And then here it's highlighting the little bird's feet. And then the network is saying, well, I think this part of the bird looks like this part of that bird. And I know that bird. That's a prototypical clay-colored sparrow. And it gets a certain number of points for each comparison that it makes. And it adds up all those points and figures out that it has a lot of points for the clay-colored sparrow class. And so that's why it classifies it as clay-colored sparrow. And then this is not a post hoc explanation. The network is actually looking at, doing these comparisons, and it's getting the points from the comparisons, and those points are what's being added up. So it's actually intrinsically interpretable. Okay, so everything is learned, by the way. The prototypes are not chosen by humans. They are learned. They're as part of the algorithm that's trained. These are training images. All of the ways of doing these comparisons, that's all learned. Everything is all learned by this algorithm. And so because the network is doing this looks like that, and this looks like that, and this looks like that, and this looks like that, we just decided to call the paper this looks like that. Okay, so this paper, this looks like that. Okay, so what it does is that it allows you to start from your favorite black box convolutional neural network, which scans the image and looks for information. And right before the last fully connected layer in that neural network, it adds a special prototype layer to that network that forces the network to do this kind of case-based reasoning, do these kinds of comparisons. And as I mentioned, the prototypes and all the ways of doing comparisons are learned. So let's take our sort of standard black box convolutional neural network, which usually is drawn kind of like that. And then just before that last fully connected layer, we would add this prototype layer, which scans the image, looking for parts of that image that look like each of the prototypes. And then it does that similarity calculation and weights them and adds them all up. So I'm going to show you what this whole part of the network is doing. So I'm going to show you exactly this whole thing. I'm going to show you on the next slide an example of how that calculation is done. Okay, so why is this bird classified as a red-bellied woodpecker? So the network says, well, I think that part of the bird looks like that part of this bird. And that is a prototypical red-bellied woodpecker. And there are two numbers associated with that calculation. There's the distance between this and that, which is that 6.499 up there. And that's a very high score because I don't know if you can see this, but this bird has a bright red head. Okay, so it's a bright red head surrounded by a white bit and then a black bit in the middle. And this is very like, the network's like, oh, I see something. So it's giving it a lot of similarity points. And then this other number over here, that's called the class connection weight. And that tells you how important this prototype is for the red-bellied woodpecker class. So each of the prototypes is like at varying levels of importance. So each of them gets like an importance score, which is this column. And then the distances between here and here, that goes in this column. And then we have 20 prototypes per class in this application, and the user can set the number of prototypes they want. then we add up the 20 numbers, and it gives us a score for that class. And we do this for all the classes. So the next highest graded class here is the red-cockaded woodpecker class. And in this case, it seems that red-cockaded woodpeckers don't have red heads. And so the network doesn't get as many points because it can't compare the head of this woodpecker to the head of any of the prototypes. And so it just gets a much lower score. It does manage to compare the feathers, like apparently like the patterns on the feathers are similar. And so it does get like a whole bunch of points from that, but it just can't get up to that score that it gets from looking at that bright red head. Now, the network does not always get everything right. This is a case where it got it wrong. And we were looking at this, trying to figure out what happened, because the nice thing about these networks is that they're interpretable, so you can troubleshoot them. So as I mentioned, you can use any black box convolutional network and transform it into an interpretable network. So here, this is a DenseNet 161 that was transformed, and it got this guy wrong. And so we were looking at this going, what happened here? Like, oh boy. So it's using the bird's eye, but as you might notice, it's kind of carefully avoiding the bird's head, like top of the head. It's kind of avoiding that. And it's getting some similarities on the feathers and so on. And it gets a few points. It's misclassified it as a Wilson's warbler, so it thinks it's a, it's misclassified it as a prothonotary warbler. It's actually a Wilson's warbler. I told you I knew nothing about birds. Okay, so yeah, it just doesn't get that many points for Wilson's warbler. And then here's the comparisons on the prothonotary warbler class. And from my perspective, well, it's seeing similarities of the eyes to the beak and so on. And to be honest, that looks like that. Like, to me, it looks like that class. But it turns out that if you switch neural networks here, if you switch the networks to VGG16, so we switched our base model, this one actually got it right. And so we were wondering, like, what happened here? How come this one was right and the other one was wrong? And as it turns out, I don't know if you can see that, but the Wilson's warblers tend to have a very black head, whereas our warbler does not have a black head. And so I think what might have happened is that this is potentially like a baby Wilson's warbler and hadn't developed that black spot on top of its head. And so the way we would fix this problem is by adding more baby Wilson's warblers to our training set. And then maybe the next time around, it could use the baby Wilson's warbler as a prototype and be able to classify this bird correctly. Now, back to the accuracy interpretability trade-off. So we've been playing with a benchmark data set in computer vision called the CUB 200. It says 200 classes of birds. And the original black box accuracy is between 74.6 and 82.3%. So this is just, send in a whole bunch of black box neural networks. Those are the accuracies you get. If you change all of those black boxes into our interpretable ones, you actually get accuracies within the same range. And then if you stack the interpretable ones together, you're still getting a network that's doing case-based reasoning, but the accuracy is better than all the black boxes. So I have yet to find a domain where I actually need a black box. So this is, even for computer vision, where the deepest of the deep neural networks are trained, we can still have an interpretable model as the same accuracy as a black box. Okay, so we did this, and we were like, okay, now that we've proven our point, so the computer vision people will leave us alone and not tell us that there's a trade-off between accuracy and interpretability, what can we actually do with this that will help people? So we decided that we would try to work on computer-aided mammography. So as you probably know, or well, maybe you don't know, the radiologist taught us all this stuff. So they said, breast cancer is a leading cause of death in the USA. There are hundreds of thousands of cases diagnosed in the USA each year, causing tens of thousands of deaths each year. Mammography is the hardest task in all of radiology. It's hard for humans to do. Radiologists miss a fifth of breast cancers. Half of women getting an annual mammogram over 10 years will have a false positive, and up to 3/4 of biopsies come back as benign. In other words, these are potentially unnecessary surgeries. Now, So we made some friends to be able to work on this problem, as you figured out. So we have a bunch of radiologists helping us. And so here's what we did not do. We did not do a black box. So here's a breast lesion over here. And this is a black box telling us the probability of malignancy is low and predict benign because, and I'm not going to give you any reason. We also didn't do a saliency approach. So a saliency approach says probability of malignancy is low, predict benign because, and then it just highlighted the lesion. It's like, I knew where the lesion was. That's why I gave it to you to look at. So it didn't give us any information at all. So what ours does, ours is called the Interpretable AI algorithm for breast lesions. And what it does is it highlights different parts of the lesion, and it gives us information about how it looks compared to prototypical lesions of different classes. So here, for instance, in the top part of that lesion, the algorithm says, well, I think that looks like this indistinct margin class. Indistinct margins are bad, so I'm going to give it half a point. Whereas the bottom part looks kind of circumscribed. Circumscribed are generally not malignant, so I will subtract some points from the malignancy score. So it's doing all these comparisons of different parts of the lesion to these prototypes and giving us points for each of them. And an interesting thing about this is that, again, we are not having any accuracy loss over black box models. And in fact, the opposite, our methods are actually doing better in some sense than the black boxes because we've been able to troubleshoot them. So here's a case with a circumscribed margin. So here's the mammogram, here's the lesion. The algorithm highlights different parts of it. And this is just the highlighting here. And it says, this looks like that. And then it gives us the similarity scores. And then it adds all this stuff up. And that's how it works. Okay, so it's exactly what I was just showing you. And here's the paper in case you're interested in looking at it. So we were thinking, okay, well, where might black boxes actually be more accurate? Can we actually find a domain where that's true? So we've already talked about like computer vision where, you know, this is, like I said, this is the sandbox for deep neural networks. And in real computer vision problems, on benchmark data sets, we've been able to see that there's no loss in accuracy. So what about just other really hard benchmark data sets? So, okay, fine. You want to talk about benchmark data sets? Let's talk about benchmark data sets. Okay, so this is a great benchmark. This is a data set from the Explainable Machine Learning Challenge. Okay, there was exactly one Explainable Machine Learning Challenge. And this is the data set from it. And this data set is a loan data set. It was provided by FICO. And your goal is to predict whether a person will default on a loan based on their credit history information. So they gave you about 10,000 loan applicants and all kinds of information about their credit history. And so what we did was we ran a whole bunch of black box algorithms on this data set just to see what accuracy we could get on it with the black boxes. And the best accuracy we got was about 73% from boosted decision trees and about 0.8 AUC. So AUC is another metric for the quality of a classifier, which in fact I will talk about on Thursday. But in any case, so those are the two metrics we want to preserve when we try to make our model interpretable. Okay, so the first place award for this competition went to IBM. Now, IBM actually created a model with only 6 questions in it. So it was a tiny little model. And there was an issue, though, with IBM's model. So they lost a little bit of accuracy, which, you know, okay, fine. They lost a little accuracy. But the thing about it is they lost a ton of AUC. Now, AUC ranges between 0.5 and 1. So to go from 0.8 to 0.62 is really, really bad. It makes the model unusable. So this, to me, I would not consider that a success. Okay. Now, I want to tell you that, like, when we were doing this challenge, we didn't know they were looking for sparse models. So in fact, what we did was that since we couldn't actually talk to a domain expert, like when you're designing an interpretable model, you really want to talk to a domain expert, find out what they think is interpretable. You know, what constraints should I put on this thing? But we didn't have that access. So we went to the FICO website instead, and all we found there were like neural networks. So we said, we're not going to use a neural network. So what do we do? So we thought, okay, what we'll do is we'll build a model that looks like a neural network, but it's not. It's actually a whole bunch of like sparse logistic regression models stuck together to look like a neural network. So that's what we did. So our entry, which won the FICO Recognition Prize, we called it a 2-layer additive risk model. It's a fancy name, but the truth is it was just a bunch of tiny little itty bitty models stuck together. It was 10 tiny models plus one final scoring model that put it all together. And we actually got the same accuracy and AUC as the best of the black box model. So we didn't sacrifice any performance at all. So what I'm going to do, I was just thinking that I could actually show you the website where this model is hosted, but I don't know if I have time to do that. I think I won't. I think I'll just show you what I have here. Okay, so what I'm going to show you here, so this is all the features. These are all the credit history features. And then there are 10 subscales here. And I'm going to zoom into this. Actually, maybe I should show you. I don't know. We'll see. We'll see how it goes. Okay, so I'm just zooming into the middle of this demo because it's actually an interactive demo. And I've zoomed into the delinquency subscale, which has only 4 factors associated with it. Were there other, I don't know what that is. Other covariates? No, those were all the covariates. Okay, great. Okay, so the delinquency score used only 4 variables. Okay, so I'm going to show you an example of that evaluated on someone's credit history here. So this person had the percent of trades never delinquent between 59 and 84. So they got some delinquencies, they get some points for that. Month since most recent delinquency, oh, they were delinquent in the last 8 months, they get some points for that. And then we add up the points, send it through the logistic function, and we end up with a risk of 79.8% just for the delinquency information. And so we have a model like that for each of these, for each of these sort of, all of the different subscales have just between 1 and 4 factors. And then there's a final model that uses all 10 factors from the subscales and adds them up. Okay, so it's really just like a bunch of tiny little additive models. Okay, so what we found was that even for really hard benchmark data sets, the interpretable model's accuracy was equal to the black box accuracy. So now we have really no scientific evidence that there's an accuracy interpretability trade-off at all, right? So you don't need to sacrifice predictive performance for interpretability as long as you're good at optimization and you optimize for interpretability in addition to accuracy. And so, yeah, so we were really excited about these results. So they wrote this nice thing on the website about acknowledging our submission for going above and beyond expectations with a fully transparent global model and so forth. We got excited about it. So we thought, okay, let's submit our paper to a special issue of a journal that was coming up, right? So we were told that if we wanted to submit this, we had to email the editor of the special issue and ask for permission, okay? So we wrote an email, dear fancy esteemed professor at fancy esteemed university. We wrote this model, created this model in this data set. We don't know whether our paper fits into the scope of the special issue. It's not a traditional methodology paper. Its contribution is an analysis of the FICO data, including a machine learning model that's interpretable. You don't need to explain a black box on this data set, even though the competition organizers told you to do it. And it won this nice thing. And so could you please let us submit our paper to the special issue? So he wrote back and he says, dear Cynthia, thanks for reaching out. This is an interesting paper, but I'm afraid it's not a good fit for the special issue. It's also related to my own recent work on explainability of neural nets. Is the FICO data set still available? And if so, could you share it? And I thought, like I just told the guy, you don't need a neural network for this data set. You can do it with an interpretable model. And he sends me a reply saying, "Dear Cynthia, I don't care about your work, but could you send me the data so that I can create a black box and explain it?" Anyway, so people really love their black boxes. Okay, so I finally got sick of this happening. And so I finally wrote a paper, and the paper, I mean, it had please in the title earlier, and the editor made me take out the please. So now it's more commanding, like, to stop doing this, like, don't do it. So it's called Stop Explaining Black Box Machine Learning Models for High Stakes Decisions and Use Interpretable Models instead. And I gave a lot of reasons, and I'm just gonna tell you some of them. And it's basically like the reasons I just told you, plus several more. So first, black box models still force you to trust the data set. I've never met a data set of like a real data set that I could trust. Okay, so, you know, if you create a black box on a data set, you still got to trust the data set. It's not a good idea. Like I'm fine with like black box, like, you know, when you drive your car, you don't know how every gear works, but that's not based on a data set, right? Data sets are messy. Okay, and the second issue I call double trouble, which is that if you're explaining a black box, you have to rely on two models instead of one, the black box and the explanation model. And if either of those goes wrong, then you can't trust whatever the prediction is. And of course, they disagree with each other exactly when the predictions are difficult. So, and these models always have to disagree with each other. They can never be 100, these explanations can never be 100% accurate. Because if they were, you could just throw out the black box and just use the explanation as its own interpretable model. So they have to disagree with each other. Okay, so how often do they disagree with each other? Well, if your explanation's right 90% of the time, that means it's wrong 10% of the time. So that means 10% of the time you can't trust the explanations, and that means 10% of the time you can't trust the black box predictions. So, and as I said, usually those predictions are the ones that are like, oh no, I really need an explanation for this one. Like all the rest are easy. Okay. Also, we have issues that sometimes these explanations are not really explanations. They don't use the same variables. And I went into a lot of detail in this paper about a scandal that happened a couple of years ago, where the ProPublica media group accused COMPAS of being racially biased in the sense that they said that COMPAS depends on age, criminal history, and race. However, their analysis was wrong, because what they did was they took COMPAS, which is a proprietary model, and they approximated it with a linear model. The linear model depended on race, and then they went and said that the black box depends on race. But you can't do that. You can't approximate one model with another and say that that second model's variables, actually important variables, are the important variables of the first model, because it might be completely different, right? It just depends on the correlations. And then, of course, the most powerful argument, from what I can tell, is that if you can produce an interpretable model, why should you explain a black box? Do you really want to extend the authority of the black box, or can you simply replace it with something that you can understand? All right, so yeah, and you know, for high stakes decisions, you really don't. Okay, so here are the papers that I talked about during this talk. There's the Please Stop Explaining paper. These two papers here, the one at the top is our interpretable neural network algorithm. This looks like that. And then this is the application to mammography. Here is the 2 helps 2B score paper and the algorithm that created that solves that mixed integer nonlinear program. And then this is the most recent algorithm on decision trees. I actually talked about some of this stuff this morning. And this is something we did as an extension of the Corals algorithm that I showed you its performance on COMPAS data. And then the paper that's right here is actually a review paper on interpretable machine learning. So if you are a technical person, you want to learn about the challenges in the field of interpretable machine learning, you can go ahead and take a look at that paper, and you'll find a lot of open problems there that you might be interested in working in. All right, thank you very much.
Inspiring, interesting lecture. You want to take questions? So was a question in chat.
Yeah, there's a
maybe
couple
wanna
in the
take-
chat. Let me see if I can grab them. Okay, great. Okay. You like data set. Oh, were there other contest criteria? Why did IBM model get first prize if they didn't have highest accuracy AUC? So the answer is that the judges didn't really know what they were doing. They actually, we designed this. Let's see if I can. How do I get out of this? Okay, so let me end show. That's what I want to do. So we designed this like gorgeous interactive tool that is sort of buried somewhere in my screen here. No, not there. Here. Okay. Great. Okay. Hopefully that'll work. Yeah. So we designed this interactive tool here where this is our model, and you could enter in the information about the person. I don't feel like entering all the credit history features, so I'm going to grab one of our demo guys. And then you could just run the model off of the Duke website here. So I'm just running, I just ran a whole bunch of optimization stuff over at Duke. And then it creates the model predictions. And then here's that delinquency score that I showed you earlier, where it pops up like this thing. So the judges decided after we submitted all this that they weren't allowing any visualizations. So I think part of it is that we got disqualified. Yeah, without that being in the rules. Okay, next question. In medicine, there's a large differential between number of machine learning models developed and the ones actually utilized in patient care. Good point. It seems reasonable that explainable, you mean interpretable, machine learning models would be more likely to be implemented, but has that been shown to be true? So I believe it is true in the sense that the most widely used models in medicine, like I was telling these guys, like the APGAR score and the CHADS2 score, these are all interpretable models. They generally haven't been created by data. They're usually created by a team of experts and validated afterwards on data. And I think the new advances in being able to create very sparse, very accurate models will make a difference in getting these models used in practice. I really do think that. That's a good question. Yeah.
Comment on the prototypes are identified and how you ensure that you aren't identifying like environmental features.
Okay, that's a good question. So the question is, how are the prototypes identified, and how do you prevent yourself from identifying environmental features? So the answer is, we don't prevent it from identifying environmental features, and sometimes it does, because sometimes those environmental features are really useful. So for instance, with water birds, it very often gives us prototypes that are just water, which is not what we want. And so we can prune those prototypes out and not use those. But how are the prototypes learned? So there's a technical answer, and I will give you that technical answer. So the prototypes are actually points in the neural network's latent space. And because we want those prototypes to correspond to training images, the way the algorithm works is that the prototypes kind of float around in the latent space as they're being optimized. And then we project them onto the training set. And then we let them loose again and then project again. And so we do this repeatedly until they've converged to, to something that is as accurate as we can get it. Yeah, good question. Yeah.
What do you see as the most promising avenues to interpretable models in a domain like language modeling? Or do you see that as interpretable models aren't as important to developers?
Okay, so language modeling is interesting because, so I have a continuing debate with a former student of mine. So I had this wonderful undergraduate who was working on prototype vision neural networks with me and then decided to go into natural language processing in graduate school. So he's over at UNC, I'm at Duke, so we're like 20 minutes away from each other. And we have this ongoing debate where I'm saying to him, I don't think you need interpretability in language models because language itself is interpretable. And he's like, no, Cynthia, you really need interpretability in these language models because they're really hard to troubleshoot. And I'm sort of maybe coming over to his like way of seeing things, because right now we're just fighting with GPT-2 to try to generate poetry. It's just such a big pain in the butt. So, you know, I think for troubleshooting, it might help to be interpretable, but I'm not sure what form that'll take since I don't work in natural language. Yeah.
How about this plank program? It plays very well, and you want to learn. You stated some fact that you can always run an interpretable model on any machine learning. What was that fact that you was?
Well, what I said was that there's no scientific evidence for a general trade-off between accuracy and interpretability. You can always construct a fake example, like a game, where you actually have to do a super complicated calculation to get an accurate model. But if you have to go that far to get, you know, to go that far out of the real world to get that kind of, you know, trade-off, then I've proven my point very nicely. Yeah. So for chess, though, interestingly, I did talk to a company that had designed a model that was trying to figure out chess strategies. So
Like AlphaGo playing, and then somebody, the grandmaster, learning from that.
well, it was chess. Yeah, it wasn't Go. I don't know how I mean, AlphaGo that's its own thing. I mean, it's not clear whether some of these games do have interpretable strategies. But that's maybe, and like things like protein folding, right? People are trying to figure out how those algorithms are actually, you know, what their decision-making processes are. I think some of those problems are sort of up in the air right now, whether we can construct interpretable solutions. But in the vast majority of problems like healthcare, criminal justice, loan decisions, you know, finance decisions, you're not really sacrificing anything. Yeah, Linda?
I'm wondering if an interpretable language model would actually help you detect fake news.
I think you could detect fake news, and it doesn't. I don't think you necessarily need a super fancy language model for some of that fake news. I think some of the generated text, and well, it depends what you mean by fake. So if you mean fake in the sense that a generator generated it, you could probably figure that out without a fancy algorithm, and it could be interpretable. But if it's fake in the sense that the news is actually fake, that might require a little bit of, you know, sourcing of information, you know, what source did the information come from? And then in that case, you could still design an interpretable model that would tell you that these sources tend to be real and these sources tend to yield fake news.
About the this looks model, for the earlier discussion of one of the other models, you said how it like 2 or 3 times more patients were able to be monitored and things like that. Did you get sort of similar follow-up results about the impact of the this looks like that when you applied it to the cancer detection problem?
Okay, so the mammography project is sort of, we've been working on it for a couple of years, and we're about to launch a big user study to actually find that information out. So believe it or not, these validation studies sometimes are even more difficult than actually building the model in the first place, because you have to get another source of data. You know, so for us, we've got to get a whole bunch of radiologists to score the quality of our results and so on. So it's a big deal, and it requires a lot of humans. And so we're just gearing up for that right now. Yeah.
So I'll read a question from John.
Okay.
Deep learning image classification work is the base deep network solely telling the image comparison layer and what to compare with. What is more information from the base deep network used in the classification decision?
Okay, so the network with the prototype layer is all being trained jointly. So the comparisons are being done in the latent space, but it's not like the black box's latent space. It's now my interpretable algorithm's latent space. So the base deep network is only used as a starting point, and then you change it, and then you retrain it completely so that it's actually a whole new network. So the question in that sense is, you know, I think I've answered the question. Yeah. I saw another one. Yeah.
Can you talk a little bit about troubleshooting interpretable models and overfitting? Is there a connection there at all? Or am I?
Yeah, I mean, I got into this whole field because I was working on power grid reliability in New York City. I was trying to predict whether a manhole would explode or have a fire based on the age of the electrical cables inside it. And I was working with the power company. And at some point we noticed that there was a feature that was being used in one of our models that was being heavily used. And that feature was the number of neutral cables in a manhole. And we brought this to the power engineers and said, it's kind of funny. I mean, what do you think about this? And they said, there's something wrong with your model. And so the only reason we were able to troubleshoot that was because we could actually understand which features were being used. And so we were able to remove that feature and put in, okay, no, we're only going to talk about cables that carry current because we were actually overfitting to a problem that was with the data set. They had given us one snapshot in time of data. And so it turns out that whenever they fix a manhole, they change the number of neutral cables. And so we had a lot of like what's called leakage, where information from the label was seeping in through that feature of number of cables, neutral cables. So once we took that feature out, then we were no longer, leaking information, and we were able to predict more accurately into the future. Yeah.
I have a question. When you're doing these testing these data sets for the parole or the credit scores, I guess there's some bias because, for example, people who are never given parole, we don't know what their likelihood of going back to prison is. And for these, I guess for these credit scores, like you're basing these data sets on people who already were given credit by some other algorithm, right? So you're sort of, the data sets are somehow, they're not like uniform samples of random people. Is there some bias from this?
So let's see. So, I mean, every data set's biased, and criminal justice data sets are particularly biased. But okay, so let me try to answer this in as complete a way as I can. So if you're talking, so let's talk about like low risk people, right? Because if it's high risk, they're, if it's someone who's high risk, they're not going to get granted parole. What? Yeah, so it's recidivism within a 2-year time frame, right? So there's bail decisions and parole decisions, and these are 2 different things. And you have to be very careful which populations you're getting data from on both of them. And we've seen cases in the past where actually like the wrong score was being used for the wrong thing, which means it was all trained on the wrong data set, and that's in the real world, which is quite bad. But the data set that we were working with, I don't think that problem is that bad because all of these people, they were all sort of released and given enough time to actually be arrested within that 2-year time frame. Most people don't stay in prison for that long in this data set, but you do have to be careful about that information in other data sets. And we did a very big recidivism paper recently where we were asking for exactly that information, like how many of these people were in prison during this whole time period. And we were told by, we were working with data from Kentucky, and we were working with the people from Kentucky. And we asked that exact question to them, and they said, just assume that people are not in prison for that time. Just assume that they're not, because we don't have that data. And they're mostly not. So it's a complicated question with a complicated answer. Yeah.
Any other questions? Thanks, Cynthia.